Russell is a third-year medical student at Robert Wood Johnson Medical School. He completed a Bachelor of Science at Lehigh University, in which he majored in molecular biology and performed research on muscular dystrophy and bacterial phages. He was diagnosed with FSHD at the age of 15. Russell's current medical interests include cardiology, oncology, and neurology. Russell's personal interests include hiking, educating, traveling, and scuba diving. So Russell, I'll hand it off to you.
All right, thank you, Lexi. And thank you guys for coming and everyone who's watching. Thank you so much for having me. It's an honor to get to talk at an event like this. As she said, my name is Russell Caratenuto. I'm a third-year medical student at Robert Wood Johnson. And today we're going to briefly talk about my path into research in medicine. And then more importantly, because I don't want to talk about myself too much, more importantly about some of the science behind the up-and-coming medications and drug therapies that are right on the horizon, and why I think we should really be excited, because I think the future looks really bright. And my goal today is to really translate that research and those findings so that we can understand them all together. All right. So my journey, if I could, see, there we go. My journey with the FSH Society started shortly after I was diagnosed. I was diagnosed at 15, as Lexi said. And then I was first acquainted with the FSH Society by starting a fundraiser for my school's high school volleyball team. I had the pleasure and privilege of doing this with my coach, Gregory Rutz, over there in the corner. And it was through this event that I met June, and we, kind of your basic fundraising event. We had a big game, we sold food, we made those shirts. It became an annual thing. We'd make shirts and t-shirts and hoodies and sell them, and all the proceeds went to the FSH Society. So it was at this point that I realized that I think I wanted to make a difference for FSH and muscular dystrophy in general, and try to, really pursue that, not just through funding, but through research. So I graduated high school in 2016, and I started college. And it was there that I was introduced to Dr. Daniel Babcock, who worked at Lehigh University. And he was kind enough to take me in as a freshman student and let me propose my own research project. So for anyone who's participated in or seen research happen, you probably know that things don't always go the way you plan, but you make it work and you do what you can with what you've been dealt. Kind of true for people with FSH too, right? We kind of have to play with the hand we were dealt. And I'll briefly explain how our research worked, and then I'll tell you all about it. So we worked with Drosophila melanogaster, which is a fruit fly. These guys in the corner, put them in, super cute. And the way it worked is we would give them FSHD, muscular dystrophy, by injecting them with the DNA for the gene that causes FSHD, DUX4. And then we would grow them up. And then once they were old enough, normally flies, they fly. We put them in a little vial, and then we would drop them down this little tube here. And then when they hit the bottom of the tube, they'd be shot out of the vial, and then they would try to fly. And, because physics, the flies can't just float out of the tube over here. They would, do a little nosedive like a plane and crash into either the side of the tube here, or they would fall all the way at the bottom. And this was meant to be a physical reading. So you can have, data points as to how strong the muscles were in the flies. So for example, if the flies had, severe muscular dystrophy like FSH, then you'd expect them to just drop right to the bottom because they can't fly at all. But if you use normal flies, for like a control group, just to test your experiment, they would fly, pretty high, and they would fly towards the top. So then to get some numerical data for this, we would take the flight sheet. It was like a little plastic insert covered in like fly paper, if you've ever seen that. We would take it out, and then you could use a ruler to actually measure how high or low they were off the ground. So then you could have, numerical data as to how strong or weak the fly's muscles were, because there's a certain set of muscles in the back here called the DLMs, the dorsal longitudinal muscles that control the wings of the fly. So as I was saying, research doesn't always go the way you hoped. And unfortunately, the flies that we did inject with DUX4 to give them FSH specifically, which was my goal, being someone with FSH, I wanted to research FSH. All of those flies, unfortunately, died. They didn't make it. We weren't able to use them for this experiment. So in research, you keep going, and we decided to go for another angle. We went for, Dr. Babcock knew I wanted to do something in muscular dystrophy. So instead, we found a mutant fly line that had a mutation in a gene called dystrophin. And sounds familiar, right? Muscular dystrophy. Dystrophin is the gene that's affected in Duchenne's muscular dystrophy. So we took the same project and we ran with it, and we instead modeled Duchenne's muscular dystrophy. And in addition to doing these flight tests, and we would do this at different time points to kind of document the progression of muscle loss over time. So we would do it maybe right when they were born, right when they were like middle-aged adults, day 14 or something. And then we would do it again at day 23 to kind of track the progressive loss of muscle over time. And not only did we do it with this flight test to have numbers for how high and low they flew, we also performed some imaging on their muscles and on their nerves. So we could actually see the differences between their nervous system and their muscles over time. And we did see, of course, that over time, their muscles and nerves got weaker. And the goal of this experiment was to first model muscular dystrophy in Drosophila and the flies, and then to look for ways to improve that muscular dystrophy. So the research I conducted in this lab is currently being written up to be published, hopefully in the next year or two. But with COVID and, I graduated college 2 years ago now, it's definitely been on its way. So unfortunately, we didn't get to study as much FSH as I would have liked. However, we still got to do a project in muscular dystrophy, and I learned quite a bit about how research works and, muscular dystrophy in general, the physiology and whatnot. So after I graduated from college, I decided to attend medical school at Robert Wood Johnson Medical School in New Brunswick, New Jersey. And I think it was at this point in my life that I realized I didn't necessarily need to dedicate my entire life to, treating and curing FSH. I had this idea in my mind as a kid that I needed to go and cure it. And, it's kind of grandiose, to be honest. It's not super realistic. No one person does everything by themselves. And also, I didn't think it was very healthy in a way. I didn't need to necessarily define my life by my illness, right? We're more than just people with FSHD, right? We're not just, FSHD patients. We do other things. Like we have stuff going on, we're human beings like everyone else. So it was at this point, I realized that from my career, I wanted to treat patients, and maybe that meant patients with FSHD, but maybe not. So I'm open-minded to see what kind of patients I may or may not treat in the future. And of course, after I tell you this long spiel about how I realized I don't need to dedicate my life, that summer after my first year medical school, I did more research in muscular dystrophy, of course. So if anyone's ever heard of CRISPR-Cas9, anyone ever heard of that? It's definitely, yes, awesome. Yeah, it's on the cutting edge of science, and it's a very exciting thing. A lot of articles from random publications like to write things like, oh, CRISPR, it's so exciting. And it is exciting. It's some of the new stuff. It's a way to edit genes. So I actually got to work with CRISPR myself and create what's called guide RNAs. So essentially you're loading a protein with RNA to cut where you want it to. So imagine you're like programming a machine to cut exactly in the DNA where you want it to. So we got to do this to model another type of muscular dystrophy called congenital muscular dystrophy. So we made our RNA, we loaded it up with the protein Cas9 and injected it into zebrafish. These are little tiny fishies, zebrafish embryos. And then we watched them grow, and then we studied them. So for example, at the bottom here, these guys did not have the injection. They were just normal fish, is what they look like. And then this one was injected with the CRISPR-Cas9 that gave it congenital muscular dystrophy. So that was the research I did over this past summer, or a year ago now. And it was a good time. I learned a lot, and it was pretty interesting too, because it was a nice marriage between research and medicine, because the mutations that we were modeling were actually given to us by families who had the exact same mutation. So this was used to help conceptualize what was going on for these families and get some more research for them. All right. So now that we've talked a little bit about myself and the research I've done, I wanted to take a moment to talk about up and coming drugs and types of drugs that are coming for FSHD, and why I think it's really exciting, and we should really be keeping our ears open and listening to what's coming out, because there's a lot of hope. So closest on the horizon is a drug called lamazimod. And this drug's mechanism is a bit complicated, so I won't go into too much detail about it. But what I will say is that it is a drug that inhibits this right here, this P38 MAP kinase, MK. And it causes a whole bunch of things. So this drug was actually used for, it's in a bunch of drug trials for a whole bunch of different diseases. So it's kind of interesting that FSHD is one of them. It was used in the past for, after someone has a heart attack, you have a risk of there being extra damage to your heart because of what's called the reactive oxygen species. It was used for that. It was being used for COVID-19, in fact, as well, because it decreases the amount of inflammatory cytokines, so it decreases inflammation. If anyone knows, when you have COVID-19, one of the main reasons you get very sick is because of the release of these cytokines, such as IL-6 and IL-1. If you've ever heard of a cytokine storm, that's one of the reasons why you get very sick and why it's dangerous. And it also has been shown to decrease necrosis and apoptosis. So that's pretty important for FSHD, right? That's what happens to your muscle cells in FSHD. They undergo apoptosis, where the cell kills itself. So this is a drug that for its trial in FSHD, it just completed, I believe, phase 2B. So that means that they would be starting up with phase 3 soon. And right after phase 3 is when it would hit the market. So I can't say exactly what the timeline would be, but I'll just say that it's definitely closer than the other drugs coming out. And it's really exciting because, there hasn't been a drug treatment for FSHD yet, and it would be the first. So it's definitely exciting. So I'm going to briefly give you a little reminder and a little quick biology lesson on how genetics work and FSHD genetics, so that we can talk about the other type of drug that will be coming out soon. That, in my opinion, is a bit more exciting. And it's especially beautiful when you consider how the mechanism of FSHD works. So briefly speaking, there is something in biology called the Central Dogma. The Central Dogma says that DNA, which is the information, in all of our cells, DNA is turned into RNA through transcription. And then that RNA is turned into protein. And then protein is what, does everything in our body. Proteins create everything. Your cells are made of proteins, carbohydrates and fats. Those are made from proteins as well. Like proteins will actually be the machinery to put everything together to make those longer structures. So the analogy that I'll be using today to explain would be to consider a restaurant, right? Let's say your body is a restaurant. The DNA would be like the restaurant's menu or its recipe book. These are all the things you can make at the restaurant. And the RNA, which is the transcript, would be like a server coming to your table and asking, hey, like, what would you like? Say, hey, I would like one order of the pasta. So they'll write that down, a transcript of what you'd like, and they give it to the kitchen, right? And then after, the kitchen will translate that transcript. They'll take that order and they'll turn it into the pasta. They'll make you your pasta, right? So does that make sense to everyone? Okay, hopefully this analogy follows. So the idea is in FSHD, we have a deletion on chromosome 4 that causes it so that the gene DUX4 normally is turned off. It's usually only on during development when you're growing in the womb. But in people with FSHD, DUX4 is turned on. And the reason is because of this deletion here. It prevents it from being silenced. So imagine you just had 1,000 orders for pasta all the time, and you just kept making pasta over and over and over again. And at this point, it's not even an Italian restaurant. You're at a different type of restaurant. Nobody ordered pasta. Nobody asked for it. And if you kept making pasta, you might run out of ingredients, might overflow the kitchen. Nobody would be getting the orders they want. It would cause a lot of issues, right? So that's what's going on in FSHD. It's a silencing error where the transcript for DUX4 should not be on, but it is. And it's making all of this DUX4 protein, which is causing cellular death. It leads to a whole bunch of different factors. And in fact, to make it even more complicated, DUX4 itself changes the expression of other genes as well, which is why it's been so difficult to study. But just briefly, this is how it works. You end up getting amplification in too much of that DUX4 protein. So the reason why I tell you all this is because one of the new ways of dealing with this that a lot of drug companies are trying to race to finish first is what's called oligonucleotide therapy. So the idea is, imagine if you could prevent those transcripts from reaching the kitchen so that the chefs can't make it. So the idea is you make another transcript that you put on top of that one, and then you can't read it. So, or you could just think of it as you ripping up the transcript. It's where the oligonucleotide, which is this blue guy here, goes in and it covers up the transcript. It covers up the order to the kitchen. So then without the order to the kitchen, you're not going to make the spaghetti anymore. So in a disease like FSHD, where you shouldn't have any spaghetti to begin with, this is a really beautiful therapy because you can prevent it entirely. So it would be a really exciting idea. And it's been in the works for a long time. And of course, talking about it just like briefly, it sounds very simple, but one of the reasons why it's been so difficult is because it's not easy to deliver a muscle or deliver a drug to muscle, right? Think about it. If you had a pill, you take it, it goes in your mouth, you swallow it, it goes into your stomach, into your gut, you might pee or poop it out. How does it get to your muscle, right? So that's been the difficult part for all this time. But there's a lot of hope because these drug companies have been having a lot of really exciting results, to say the least. So I think that we could expect these kinds of therapies to be, in later stage clinical trials pretty soon. I believe a couple of the companies should be entering stage 1 within the next year or so. So that's really, really exciting, considering that this is cutting edge science and research. All right, and that's pretty much my presentation. If anyone has any questions, feel free to ask. I tried to keep it as simple as possible, but we could totally talk about it.
I have a few questions. Oh, sorry, you go ahead.
I was just wondering, when you were your first experiment where you were injecting the flies with DUX4, was that where did you get the DUX4 from? Just people who volunteered?
Oh, so okay, that's an awesome question. So actually, there's a couple of ways that can be done. You could make any piece of DNA you want. So you can actually order it from a lab, and you can make the piece of DNA that would correspond to DUX4, and then have that transformed into a vector that then you can give to the flies. But in fact, we actually collaborated with another research lab that researches FSHD called the Jones Lab. And it was actually June from the Fsh Society that put me in contact with them. So we got the
Peter Jones, right?
Yes, yeah.
Yeah.
Dr. Peter Jones. Yeah, we got the flies from them, and we took it from there.
I have a question or two. So I hear a lot of different, drug trials talking about how they've been effective in treating FSHD. I just want to ask a little bit about what does that mean? Because I feel like that's a very broad term, to describe, oh, it's effective, but, obviously, different drugs target, different things, like one was ripping up, the transcriptions, right? Other ones are targeting, other, inhibiting DUX4 in other ways, right? So I just want to ask a little bit about what that looks like, whether it's, just what does effectiveness mean?
Yeah, no, that's a fantastic question. And unfortunately, the answer to that is that it varies on every single drug, right? Every company that's working, they're going to have different metrics. So there is no data yet for the oligonucleotide therapy, just because it hasn't happened yet. They're not ready to bring that to, they're not entering phase 1 trials yet. But what we can talk about is lemacimod. And I believe that we can look it up as well later, but they said that they had improvements, right, in people. Their metric was a couple of things. I believe it was lifting things over their head. They were physical things, like they had physical parameters. So performing certain actions, moving certain objects, loss of muscle over time. So they had a couple of different metrics by which they measured it by. But to your point, what does that necessarily mean for us as people with FSHD? And the truth is, we won't know until things go further, But what I can say is that, every drug kind of starts this way, like no drug starts, being perfect, right? Nothing ever happens overnight. So the fact that we have promising data, and interestingly enough, actually, with this particular drug, they were seeing improvements in people's function without any changes in the biomarkers. So it wasn't like there was decreased levels of DUX4 or any other biomarker they could find, which is pretty interesting because they're pretty much saying we don't even know why, but it's kind of helping. So, which, interestingly is how a lot of drugs work, especially in medical. I've learned studying a lot of drugs, the mechanism is not fully understood. And you're like, okay, well, it works though. So that's good. But
cool, yeah. If I can do a follow-up question on that, thank you for that. By the way, that's very helpful. I just forgot it.
That's okay.
Sorry. It was I know that I hear different trials again, and some have specified and said it may slow or stop progression, that kind of thing. And I just wanted to ask, with these up and coming drugs, what do you think is going to be, or I guess what results have been seen in either slowing or stopping progression? And also, are any of these, or sorry, have any of these shown any potential for muscle regeneration in some sense?
So again, when specifically for the oligotherapy, there is no human data to speak of yet, at least that I'm aware of. Of course, data changes every day, so I'm not going to pretend like I know everything, right?
Yeah.
But the general consensus is that these companies are hoping to, of course, the idea is to first stop progression and then to reverse things, right? Like that would be the natural progression of treatment.
Yeah.
And then you're asking how viable is that, or how is that probable? Like, is that probable? Is that what you're asking?
Yeah. Yeah.
I think that it would probably be on a case-by-case basis, right? Because let's say, for example, someone is more mild and hasn't been affected that much, then a therapy might help them quite a bit more, right? Because they haven't lost that much muscle. But if someone lost a ton of muscle or no longer had any muscle and had to have, some sort of surgery or some sort of, they had damaged that tissue, then they might not expect to have as much regeneration or, that much help from therapy. But that being said, I mean, even stopping the progression of FSHD, right? Like, let's say you could stop DUX4 from being produced and you couldn't gain the muscle you lost back, but you wouldn't lose any more. I mean, even that would be quite significant. And additionally, I can't speak to what the future holds because no one really knows, but I would say that it's hopeful. There's definitely hope. So
thank you very much. It was very helpful.
No problem.
Oh yeah, Russell. Oh, go ahead, Lexi.
I was just gonna say, I don't know if I maybe just missed it, but like for the last therapy, like the therapy, is that, so what is the outcome of that? I know it like stops, the translation. So what would that do for you? Is that still stopping progression? Is that like a cure, or what is that therapy?
Yeah, so interestingly, like in a perfect world, right? And that's why I wanted to outline like how FSHD works, because it's very rare that a disease works this way, where it's not like in some diseases, right? Like you have too much expression of a gene that normally you'd have a little bit, like normally you'd have 10 pastas, but now you have 1,000. In our case, you really shouldn't have any pastas. You shouldn't have any DUX4 once you're an adult. So if you were to turn it off and you were able to stop the production of DUX4, theoretically, I mean, that would be like a cure. You would no longer have progressive FSHD. You'd no longer have FSHD in that way. You would no longer be producing the, protein that's responsible for your disease. Does that mean that your muscles that are gone would come back? Nobody knows yet, right? That's why, like Jacob was saying, it's a tough question. And, I can't act like I'm an authority on it. There's a lot of research and there's a lot left to be done. But the reason why I think we should be so excited is because how lucky are we that this therapy and this method of, drug development is perfectly catered to FSHD. It really is. So it's really something to be excited about. And that being said, I'm sure that this is going to be therapy that's used for other diseases as well, not just FSHD. A lot of diseases could probably benefit from oligonucleotide therapy. So certainly exciting, because then you would no longer have production of that gene you're looking to turn off.
Sorry, Russell. I was just taking that. I was taking all that in. So when you're talking about losmapimod, I'm actually on that trial. I've been on it since 2019. It's supposed to slow down the production of DUX4, if I understand correctly. Is that true?
I believe that was their goal, which is why I think that they were surprised when they released that the biomarkers were unchanged. Like they were like, wait, like they had results in patients, but they didn't see like any reason to suspect that there was less DUX4. But I believe that's what the idea is supposed to be.
Since I've been on the drug, I mean, I've lost muscle around my legs. Like you can actually start to see my femur
Right.
from my quads down to my knees, and was kind of questioning to see that, because I figured it should at least stop any more production. Because I mean, I have areas, I'm sure, like you guys, where there are indentures in your shoulder blade, in your shoulder socket, and your wing, your shoulder blades are sticking out. I would have thought at least it would have stopped that, but I saw more deterioration while I was on the drug. And I mean, like you said, for the testing, they have that. They make you lift stuff like, they have that little Xbox thing where they measure how far you can lift. And I've been pretty consistent since starting that drug. So I was wondering if I'm at that point where, I'm not going to plateau any further. I'm just going to be on one straight line going forward.
Right. I mean, I think that, well, first of all, thank you for sharing that. And I'm sorry that that's been happening. I want to say that when it comes to drug trials, so you said you started in 2019, so I don't know if that would be a part of the phase 2B that they're discussing, or if it's phase 1, but throughout the various—
Phase 1, yeah, I was on since phase 1.
So phase 1 of a drug trial typically is not actually meant to be therapeutic. It's meant to be, phase 1 typically tests if a drug is lethal or has potential side effects for a person. So it's like proof of concept, really. So the dose you were getting may not have been necessarily therapeutic. Also, maybe it doesn't work, right? Like it's still in trial, right? It's, we can't say for certain. But that being said, as
are you trying to, because they give you either the drug or the placebo. You're trying to say that maybe I got the placebo?
So that is also a possibility. It's possible you were given placebo. But it's also possible that in an early drug trial, right, they don't give a therapeutic dose. Early drug trials are more so meant to, because, right, the point of the drug trial is to make sure not only does it work for someone, but before that, whether or not it works, they need to test to make sure it's safe. Does it cause side effects? Does it make people sick? Because if a drug makes someone sick, why are we going to, make it and sell it to people, right? That's not going to be helpful. So in early—
does that determine the amount of like how many milligrams that they give you? Because
yes. So in the very beginning, they would give lower doses. And again, I can't speak specific, like I'm not exactly sure the specifics of your trial. I'm speaking generally about drug trials, right? They will give lower doses in phase 1. And it's not— the intention of phase 1 is not to treat. The intention is to check for toxicity. Then in phase 2, which is why this was the 2B trial here, they'll look for at lower doses, do they see changes? And then phase 3 is where they're really playing with the dose to find what the actual therapeutic dose might be. Now, does that explain your specific situation? Not necessarily, but I mean, I think that's the best clarification I could hope to add with that.
Thanks.
No problem. Does that make sense?
Yeah. The only thing is because I watched the dosage from when I started, and it's that same 7.5 milligrams, and that's what I'm taking right now since from when I started to current. And and at first I thought I was on the placebo, because after I saw so much muscle loss, I was like, I'm probably on the placebo. But at the end of their phase 1 trial, I don't know if you were on that call, but they gave a breakdown on who was on the placebo based on race for ethnicity. And I was the only Asian or South Asian person on that trial. And they said that I was given the actual drug. So then that made me question it more. It's like, does the drug only work for a certain amount of, like you said, like depending on how much repeats you have? If you have more, I can never remember if you have more or less, but if it's more severe, it's probably not going to work as much. But if you're a mild case, probably going to plateau you out, which is good, better than nothing. And
yeah, I mean, that could certainly be the case as well, right? Like that could very well be how the situation is. But I guess until they continue, we won't really know, like we can't say for certain, right? Like data point N of 1 is very small. Like, one person's one data point is not enough to know larger trends like that, Does
anybody have any more questions?
Yeah, one last one. I don't know if you saw on the FSHD website on, like, I think Facebook, there was someone, I don't remember his name, he donated enough money or he said that there would be a cure within 5 years. If anybody heard about that.
Oh, this is the cure by 2025.
Yeah.
Is that the Lululemon founder? That Lululemon?
Or all I remember was like I guess he made a donation and said that there's going to be a cure within 2025, but they never. I don't remember he mentioned what type of, what track they're going down to, whether it would be CRISPR or what it would be, the other therapy that you were talking about. I don't know if you guys remember that, seeing that.
I'm familiar with the promise of the cure by 2025, and I think what is stated by that is that there will be some sort of effective drug either towards the end of trials or in the market at that time. Which, when we consider where some of these drugs are, specifically the oligos as well, it's not necessarily far-fetched to think that that could be the case. I'm not sure if that's specifically what you're referring to, but I did read a little bit about that.
There's also the guy, the former, or at least founder of Lululemon, who donated $100 million to starting his own research company. Though I know he has FSHD too, so that's what they were focusing on. But his goal is to find a cure by, I believe, I assume, but that was he's basically starting his own research company.
Well, definitely a lot to be excited about. I mean, it's I think really it's easy to, I don't know, I feel like it's easy to not realize how lucky we are that we happen to live during a time of technological, but also scientific boom. What's possible today with genetics was not possible even 5 years ago. Even when I started college versus what's, feasible to do in most labs now has changed so much. And that's crazy because it's not like I've had a career in research. I'm only 23. I'm not that. So it's pretty amazing how much is on the horizon and how much more things will probably change.
I agree. So if anyone doesn't have any last questions.
I have a quick question.
Okay.
I'm sorry. I'm actually pretty new to this. I was just recently diagnosed, and I have a quick question. So correct me if I'm wrong, but it is autosomal dominant, and I just had a question if the drugs that are being created right now would prevent our offspring.
Right. No, I
having-
totally.
Yeah.
You're asking if it would prevent you from passing on the gene.
Yeah. Mm-hmm.
So currently, no, that's not not really the mechanism by which these medications would work. But that being said, if this were a cure, then I guess you wouldn't really be concerned if you pass on the gene, right? Obviously, you'd probably not want to. But if it was a cure, a true cure, then it wouldn't necessarily matter, right? But that being said, it's something that we need to be aware of because there is no current medication that would stop you from spreading it. If you wanted to prevent yourself from having a child with FSHD or prevent yourself from passing it on, you would have to do something called PGD, pre-implantation diagnosis, where you would essentially have in vitro fertilization, and they would keep the embryos growing. And once there were enough cells, they would take some and perform a genetic test to see if you had the mutation for DUX4. And if that embryo did not, then they would implant it.
Oh, okay.
Also, if you want to know more about that PDC, we have someone who shared their experience on our Discord. I don't know if you have seen our Discord, but we believe we still have a link in our bio for that, right? So
Yeah, yes, we do.
Someone posted in there. Do you know what category that was? In case you want to learn more or see someone else's experience. But she posted about her experience with it a little bit.
Sure, yeah, I'll check that out. Thank you.
All right. Nobody has any other questions, I think we'll wrap it up. And this will be recorded, so if you want to share it with anyone or watch it later, that will be a possibility.
Thank you so much for having me, guys.